The benefit of me being here in person is seeing all of those names that you've heard of or seen on YouTube, and you get to see them in real life, you get to interact with them, you get to ask them questions, you get to understand that they're really nice people.
So hello everyone, I'm Vincent Reverdy. I'm very happy to be here at CppCon. And today we talk about high-performance numerical integration in the age of C++26. So at least that was my original intention, to talk about high-performance numerical integration in the age of C++26. But last year I gave a talk about how to build symbolic systems, symbolic equations in C++. And this was a lot focused on numerical high-performance computing. And while preparing that talk on high-performance numerical integration, I realized that because it's in C++ compared to other languages, that many languages have like libraries that are ready to use, and users can just like bring the library and do numerical integration. In C++, we tend to have to implement everything from scratch. So I started to delve into numerical integration, and I realized that I couldn't find a talk at CppCon on numerical integration. So most of the talk will be actually dedicated on the basis and the foundations of numerical integration. And I hope that you will learn some stuff. So as I said, I'm Vincent Reverdy. I'm coming from France at Laboratoire d'Annecy de Physique des Particules. So I work with physicists as a computer scientist. And I work at the interaction between physicists and computer scientists. As you will see during this talk, there will be some physics and some computer science also. So the first part of the talk will be focused on how to implement a very simple numerical integrator, so that you know in a few lines how to implement, how it looks like when you're trying to implement such a thing. And then I will go into the theoretical foundation to try to see what kind of software architecture we can do in modern C++ to try to tackle this problem. And then I will outline an implementation and maybe some stuff, and I will give some picture of what can be done in C++26. But I would say I will, compared to last year where I gave a lot of details of how to implement things, this year I didn't want to go too much into details. So first, I will start with introduction. So we'll start with an example. So the coding style may not be the best, but the goal is to try to understand what's going on. So the goal is to guess what this program is doing. So first we have some preamble importing some C++ headers. And then we have the main function that declares some constants and some type. Well, it should be, and some values. Then it declares some parameters, and it is giving some default parameters. Or it will first see if there is an argument given as an input of main, and if there is not, it will take a default value. Then it will call a function compute, and that will return some structure evolution. And at the end, it will output the last element of evolution divided by 1 billion year. And if we look at what compute is doing, so compute has a bunch of parameters as input. So it will first declare two variables. It will initialize them. Then it will initialize the vector that is called evolution, and it will reserve some space. And then it will declare a function that will be integrated. So the function is this one. So you have the parameter a times other parameters and the square root of a combination of a with different powers. And then there will be a loop that will add things to the vector and update the value of a and the value of t. And then at the end, when A will be less than epsilon, then it will return the vector evolution. And the question is, can anyone guess what the output will be of that program?
Kind of a wild guess, but like 13-some billion years into the universe?
Yes. So it will return this number. And there is a problem with this number first, which is there should be some units because a number like this, like you cannot really say anything about it. So quantity and units library would be very nice for these kind of things. So if we put the unit, then it's 13.7839 billion years. So what we just computed in a few lines of C++ is the edge of the universe. And as I said, so we computed the edge of the universe in about 60 lines of C++. So this will be the basic example that I will follow during the talk to try to understand what's going on. So we'll delve into a little bit into the details. So it returns the age of the universe, but also it computes the evolution, meaning that you can trace back to the Big Bang the evolution of the scale factor. The scale factor is typically you measure 1 meter now, and the question is how will the meter evolve? I mean, the meter of space-time evolve in the past. So at the Big Bang, then it's 0, and now we say it's by a normalization, it's equal to 1. And this curve shows that in 13.8 billion years, how it evolved. And the thing we computed is basically the outer shape of this diagram. So this is what we computed. So if we come back to the core of computation, so the function we integrated was the following one, where we had so A is the scale parameter. So we have scale times some constant times 2 and multiplied by root with some powers of A. And then, as I said, the integration is just this one. And what it does, so it computes A by taking the previous value of A and going back in time by doing A minus a small parameter h times the derivative that is computed by the function just before. And what it does, it's the most basic numerical integrator you can have. It's Euler's method, which is just the formula showed here. If you have some function, the next step will be equal to the previous step plus this parameter h times the time of function, which computes the derivative of the thing. So basically, the numerical solution will take steps and integrate the function. In our case, integrate the evolution of the universe back in time. So the equation we are integrating comes from a simplification of general relativity. So if you take Einstein's equation, which is the leftmost one on the screen, it equals the metric of the spacetime to some matter or energy content. And when you say that the universe is isotropic and homogeneous, then you can obtain a set of two equations, which are the Friedmann equations. And then when you say that the universe is filled with a perfect fluid, then with a mix of perfect fluid, then you can have the function we integrated as an evolution with a mix of several components. So as our components, we have radiation, like photons and such. We have matter. We have a curvature parameter, which indicates how curved is the universe at large scale. And then dark energy. And the equation we integrate symbolically is this one. So as you see, the dIdt in C++ just corresponds to this equation. And this is the first order ordinary differential equation. which are pretty rare in physics, because in physics, most equations are second order, but this one, it's one of the most simple I could find. And actually, we can compute the age of the universe with that. So is it the end of the story? No. Because plenty of things can be improved. So as I said, this is the simplest possible integrator. The question is, can we do better to achieve more accuracy and more precision in terms of numerical performance? The question then is, can we parallelize the code? Can we use more modern constructs? And can we make it more generic? Because for now, we have the function that integrates the thing is just dedicated to integrating the equation that trace the expansion of the universe. So we'll try to see how we can modify this program to try to do something better. So what we could do is the following. So first, we'll change the integration function. So in terms of, instead of computation, we'll put everything in a function that will be called integrate FLRW for Friedman, Lemaitre, Robertson, Walker, which is the name of the equation that I showed before. So as input, it has a lot of parameters. So this is bad style. It would be far better if we had units and if we could put everything in a single structure that would handle all of that. But for now, that's the style I took. Then we initialize some constants to be sure that during the loop, even a very dumb compiler will be able to extract the best performance. And then we initialize two values, and we initialize a container with the first value. So what we'll do, so in the previous function, it was only integrating in the past, meaning that we know how the universe is now. Now what we'll try to do is integrate both in the past of the universe and both in the future of the universe. So what we'll do is that we'll create two vectors and we'll try to do two separate integration. So I will keep the same function. The only thing I will modify with so this is a function, the Friedman-Lemaitre equation. So the only thing I will modify is that I will add a parameter sign that will help us integrate in the past or in the future. But apart from that, this is the same thing. And then we'll use an algorithm called runge-kutta of order 4, which is probably apart Euler, which is very bad for integrating things, is probably the most basic and most used integrator out there. So this function, what it does is the following. So it will take the parameter a, and what it will do is it will compute the first parameter called k1, and it will be equal to the derivative of a at the point of a. Then it will update the value of a, so it will be an intermediate step. So a1 will be equal to a plus dt over 2 times this first parameter k1. Then it will compute a k2, which will be the intermediate value of the derivative at the point a1 that we just computed. Then a2 will be equal to the previous thing, so k2 times dt over 2 plus a. Then we have a k3, which will depend on this parameter a2. Then we'll compute a3, which will be a plus dt times k3. And here there is a change because we don't divide by 2. And then we have key4, which is just a3, the derivative taken at the point a3. And then the result will be this formula, a plus dt over 6 times a combination of the several k1 and k3, k1, k2, k3, and k4. This is a weighted average of all these parameters. And then we'll change the loop. So the loop will be, so here, if you want to copy the code, it will work, but there is a lot of details that are irrelevant. So here we are just initializing stuff. Then we are starting the integration loop. Then we update T and A. And what we do here to try to not lose precision is that because we always have the same time step, so what we do is that instead of incrementing T each time, we are just saying that T is a multiple of the number of integration steps we did. And then we say that A is equal to this runge-kutta integration method, starting at the previous step. And then we are checking a lot of stuff to be sure that we are not going, that the size of the universe is not getting under 0, because that would be very weird. And in the future, we are also checking some stuff. And then what we do is that at least to get, so as I showed before in the runge-kutta function, it's a sequential process. Like all parameters depend on the previous one. So in a naive way, we cannot really improve things in terms of parallelization, but what we can do, at least in this case, is that we can integrate in the past and in the future in 2 different threads. And so we finalize by joining, and we then compiling the future and the past in the same output, and we return it. And what we can do at the end is integrate the equation for different models of the universe, both in the past and in the future. So the model that we think we are, that is the closest to what we think we are, the universe is the one in blue. So there is an acceleration in the future due to something we don't know anything about that we call dark energy. But then when you change the parameter, you can have universes that expand and then go back to 0 in a big crunch and stuff like this. And you can have a universe that completely destroy everything because in the future you have an exponential. You have an accelerated expansion that is exponential. So it destroys everything. So runge-kutta of order 4, which is the algorithm we used, basically does the following. So it has 4, as we saw, there is 4 intermediary steps that are used to try to average at best the evolution of the function. So the 4 parameters are K1, K2, K3, K4 that correspond to intermediate steps. And then we average everything. And we say that the next step is a weighted average of these parameters. And the next time, the way we update time is just we add the step size. So the code it corresponds to in a generic way, not focusing on the expansion of the universe. So step 1, we have T1 and Y1, which are equal to T and Y. Then we say that K1 is equal to the derivative. And then we do the same thing again and again for step 2, step 3, step 4, and the result. And this works with any function that is a scalar for now. We'll see after how we can improve things. So as I said, the problem is that every intermediate step depends on the previous one, which means that it's very complicated to parallelize stuff. So the first improvement we can do, I mean, the first in the exploration of integration algorithm is try to wonder how can we integrate systems of equations that are multidimensional. So we can change the runge-kutta algorithm with a vector function where y is now an array of things, and with the derivative that returns an array of things. So we start again with types and constants, and we'll just modify things to have the multidimensional version of runge-kutta of order 4. So we'll do as before. We'll have, except that now because we have a vector type, which is an array, we don't want to reallocate all the, like to create new structure, just in case the compiler would not optimize that, even though I think it would. So we have step 1 now that includes a loop on y that it does it for every member of y. And then we have k1, which takes the result of that array and puts it into the function that computes the derivative. Same thing for step 2 as before, same thing for step 3. I think and same thing for step 4. And then at the end, we compute the result by filling the vector yi for the length of the vector. For example, if we integrate an equation that is on position and we are in 3 dimensions, then the size of the vector will be the three dimensions of space. So as mathematically, what it does is that simply before we had a scalar equation, now we have a vector equation. That all that changed with here a big Y representing a multidimensional thing. So the example we can have with that new approach is the 3-body problem equation. So how can we integrate that with our new runge-kutta algorithm? So what we'll do is that we'll have 18 different vectors of size 18, because what we'll have is, so we have 3 bodies, and for each body we have the position and the velocity. And the derivative will be the velocity and the acceleration. So it's 3 times 6. So we declare, so it will take as an input an array, and it will take also as an input the value of the gravitational constant and 3 masses. So the number of dimensions will be 3. So we'll have an output vector, which will be the same size as the input. And then we'll use range. So as I said, the x position will be the 9 first things in our vector. And then we'll have for the particle 1, this will be the 3 first components. For particle 2, it will be the second 3. And for particle 3, it will be the third 3 components. And what we'll do first is that we'll compute the distance between the different particles. So we have a function for that in 3 dimensions in C++ that does exactly that. Then what we'll say is that and then we have the velocity of the things, of the input thing, that are going from the index 9 to the index 17. What we will return, though, is the derivative of the elements. So the last element will be the acceleration. So we initialize the 3 different arrays, and we will fill them with the computation of the acceleration. So we'll have A1, which will be equal to this, which is just computing the different force that, depending on the distance and the mass of the thing. Same thing for the second acceleration, and same thing for the third acceleration of the third particle. And then, so the first elements of the output, we already know them because the derivative of the position correspond to, we already had them we already had the velocity in the vector. So we are just taking the elements at the end of the input vector and put them at the beginning of the thing and the output vector. And then we copy the different acceleration components that we just computed with A1, A2, and A3. So our vector in that case, as I said, we have x, y, z for the first particle, x, y, z for the second particle, x, y, z for the third particle, and same thing with the velocity. And when we take the derivative of that, we have the velocity and the acceleration. And when we mix the two, so when we put this function into runge-kutta number 4, we can then integrate the 3-body problem. We just need to initialize position and velocity, and then it does nothing. So it's very few lines of C++ code, actually, and we are doing everything from scratch. So in reality, so this is the plots I made because this is stable orbits taken from Wikipedia. And the problem we have with the current scheme is that it cannot achieve long-term correct integration. Like if we want to achieve long-term integration, we need far better integrators. And so now what we'll do is that we'll go into the mathematical details. But for me, the important thing in this introduction was to show that the basics of numerical integration with code that you can copy and paste and start to play with them. So the context is the following. So when we'll delve into the detail, first there is an ambiguity. Because the first thing integration can refer to is about integrals. So computing integrals. So numerical integration can be seen as the computation of the numerical value of definite integrals. And synonyms of that are quadrature, or in higher dimension, this can be cubature, sometimes called. The other things are differential equations. Numerical integration can refer to the name of numerical methods for ordinary differential equations, and more than that, differential equation solvers. So the term integration can go beyond ordinary differential equation and can include many other types of differential equation, like partial differential equation. So in the case of an ordinary differential equation, what we have is an initial value problem, and we have a formula that returns the derivative of y as a function of t and y of t, and an initial value. And this can be in n dimensions, in this case, d dimensions. So, but the reason why it's called numerical integration is that there is an equivalence between the two, because finding antiderivatives is like solving an ordinary differential equation. And we have algorithm to do definite integral that works well, like Gaussian quadrature, Clebsch-Curtis quadratures, and other types of quadrature. And for ordinary differential equation, there are plenty of different methods, like Euler's method that we saw, runge-kutta methods, Euler's method being a subtype of runge-kutta. We have things like general linear methods and other stuff. And so this talk, in this part, then I will focus on ordinary differential equations. And in all the following, integrators mean differential equation solver. So if we look at the lens of differential equations, it's a lens with many different like parts. Like there are like ordinary differential equation, but also algebraic equation, stochastic equation, delay equation, stochastic differential algebraic equation. There is a whole literature on different types of differential equation that needs different solvers because they all have different properties, and you will not try to optimize them in the same way. So, and the reality goes way beyond this map. Like if we go to partial differential equation, then there is a whole land of different like other types of differential equation. So on this talk, I will focus on ordinary differential equation because they are already complicated, and I think it gives a good impression of what is required to solve these equations. And as I said, many techniques can be extended to other types of solvers. So if we look at other language, like other language have library. Many language have libraries to integrate ordinary differential equations. There is CppCon integrate in Python. There is differential equation in Julia, and in C++ we have oddint in Boost. The thing is that oddint dates the last copyright date from 2015, and a lot happened since in C++. And if we compare to what is done in other language, we are really lagging behind. For example, in Julia, it's very impressive because they implemented, like they have probably 100 different types of integrators with different properties. It's very generic. You can load them on GPU, like it's very nice. And we cannot do that in C++ currently. So I will not show in the following how to revolutionize everything or show a library that will beat everything. The goal is just to see the foundations that will allow us to build a library and show a path forward using basic examples. So we have to understand what's going on, we have to do a little bit of math. And this is something like, because in a lot of libraries, everything is implemented. In my experience, most people don't delve into the details and don't really know where it's coming from. They just use a library that works out of the box. And there are many, many interesting things when we open the box and look what's inside. So the problem statement is that we'll have an initial value problem, which is just what I said before. We have an ordinary differential equation and an initial condition in d dimensions. And then the question will be, how can we abstract the problem we want to solve? So the thing is that when things are well posed and well abstracted in mathematics, is generally, not always the time, but it's generally easy to abstract in software. So because you can take the mathematical architecture and convert it into a software architecture. So that works when the math are understandable, I would say. So an example, and that's a good example of why implementing units doesn't work, because currently, and it's very complicated, because units are intuitively understood in physics, but if you go to mathematician and try to look at the foundation, units have very fuzzy foundations in mathematics, and you still have papers in 2024 with mathematicians debating on what units really are, what types of mathematical abstraction they correspond to. But my guess is that if we had a very reliable foundation in mathematics, then it would be far easier to implement units for C++ and for software libraries. So the question is, okay, so as I said, there are good mathematical foundations for numerical methods for ordinary differential equations. And the good thing is that you don't have to look in like 10,000 different papers to have that. There is a mathematician who worked on that during many, many, many years. He has been an expert all his life. And he wrote a book, the last version of his book dates from 2016. And the good thing is that he talks about how to represent the problem in a generic way. And that is very useful for programmers, because if you have a mathematical abstraction that works in math, it will very likely work in like software too. So in his books, he said that there are different classes of algorithm. The first class of algorithm, like the one I showed before, are runge-kutta methods that can be expressed in this way, where we have the next step, n plus 1, is equal to the step before plus the time step times a sum with these k parameters, where every k depends on previous k's. Then we have linear multi-step methods that can be written in this way as sum between, on one side, sum of ag, y, n plus g, and on the other side, bj times the function. And then we have general linear methods that are way more complicated because they depend on more structures. But you have a very general framework, and they can be expressed in that way. So these are different approaches with different properties. So runge-kutta method, they generally use intermediary steps, and the thing is that they discard the information. You don't reuse the information at the next step. And you only need, I didn't finish the sentence, it only needs the previous step to compute the next step. Then linear multi-step methods, LMMs instead of LLMs. So it takes advantage of previous steps to improve efficiency. And then we have the general linear method that can combine advantage of both approach. So both having intermediary steps and taking advantage of previous steps. And then we have two kinds of methods in each of these three different methods. There are the explicit methods. And what they do is that the solution at the next time step is computed only using the information from the previous step. And this is very nice for like equation that behaves well, but when you have stiff problems, meaning you have equation that can vary quickly, then they're generally not very well, not a good fit for that. And then you have implicit methods, and in implicit method, the solution is defined through an equation that includes the unknown of the future value. So at each time step, you have to solve a system of equation, and it offers far better stability for stiff problems. So you have to evaluate what kind of problems you want to solve and choose the method regarding to the type of equations you have. So Butcher, the mathematician I showed before, designed a kind of a universal abstraction to encode runge-kutta method, at least for runge-kutta method. And it's called the Butcher tableau. And it has like a main matrix A, and then a vector C and a vector B. So AJ, you can see that the matrix is lower triangular. So Aij are coefficients, Bj are called the weights, and Ci are the nodes. The node correspond to which intermediary steps you will choose to compute your vector. And S is the number of stage you will have in the function. So when you say you have a fourth order, then you will have S will be equal to 4. So you cannot take arbitrary values for all of that. The coefficients, weights, and nodes have to be carefully derived because for each choice of these constants, you will have a particular method with different properties. So this is for explicit runge-kutta methods. But also we can have adaptive methods. And because for now, what I showed, the time step is always the same. But what we would like to do is when depending on the error we are making, we would like to shorten the time step so that we can get higher accuracy. And a way to do that is instead of having one vector B, is to have two vector Bs and compare with different orders and to compare the results. For example, if you have the first one, which is order 4, and the second one, order 5, then you can observe what kind of error you're making at each time step, and you can configure the time step to try to improve that. So the error, you can, as I said before, the error estimate is equal just to the difference of the time step you're computing with the two different B vectors. And then you can have implicit runge-kutta methods. And the difference with implicit method is that now the matrix is not lower triangular. So this is the most generic matrix for runge-kutta method. And in that case, at each time step, you will need to solve this equation. So the second types of methods are linear multi-step method. So what I showed before is really the abstraction where you can encode, with this abstraction, you can encode all runge-kutta method. So then we have linear multi-step methods. So they are specified in the following way. So in linear multi-step method, you try to compute the current value based on different previous values. And basically you have a vector alpha and a vector beta, and you combine them with the evaluation of the previous values and the previous derivatives of the values. And the method is entirely specified with alpha and beta, which can be seen as polynomials. And then there are general linear methods, which are way more complicated. And Butcher has found out a way to represent them in a generic way. So you can encode all general linear methods as a matrix of A, B, U, and V with different sizes. So A is S by S, B is R by S, etc., etc. And then you have systems of equations and with intermediary steps that depends on the coefficient of these matrices. And you can summarize that as a linear algebra equation that you need to solve. So the good thing is that the tableau I showed before, the Butcher tableau, which was used for runge-kutta methods, you can encode it as this matrix representation. So runge-kutta method it can be seen as a subset of this very general abstraction that is just a matrix of coefficients. And linear multisteps with the alpha and beta can also be seen as a specialization of this general abstraction. So with all of that, depending on what kind of coefficients you have and what kind of A, B, U, and V matrix you have, then you can derive methods which names are well known, like Euler, Runge, runge-kutta, Feldberg, Lobano methods, Rado methods. Like you can derive all of that from this abstraction. You can also derive linear multistep method with the backward differential formulas, Adam-Basforth methods, and Adams-Moulton methods. And you can also derive general linear methods that are less used and there are way less literature on them, but they are very fancy and you can specialize them for certain types of complex problems. So because we have this abstraction in math, then we can guess it would be a very good idea to use this matrix A, U, B, and V as a foundation for the software architecture. Because if you have the value of the coefficient of A, U, B, and V at compile time, then you can basically generate all the algorithm with the same interface. In terms of concepts, in terms of software architecture, that would be very nice. So because I only have like 17 minutes left, I will not go into the details of how we can actually implement like something high performance with that, but I will give an impression of starting from there, how we can implement something that could be fast enough. Like what do we need to do to achieve high performance with this kind of abstraction? So instead of using a general linear method, we'll focus on the runge-kutta subcase because it's easy. Like the same kind of methods can be used in both cases in terms of not numerical methods, but in terms of abstraction. They rely on matrix and tableaus with coefficients and things you want to do at compile time. So a reminder of the Butcher tableau that represents runge-kutta algorithm can be expressed in that way. So we see that we have a two-dimensional array A, we have a 1D array C, and we have two, depending on whether we have either 1 or 2, depending on whether the algorithm is adaptive or not, vector 1D array B. So to try to see like what we can design with this approach with a concrete example, we'll use an algorithm, not like the most used algorithm in runge-kutta or generally like runge-kutta Feldberg or runge-kutta adaptive method 4 and 5. Here, what we'll target is called Werner's most efficient runge-kutta methods. This can be found on this website. And what this website has is a bunch of coefficients for methods that are supposed to be like very efficient and very like high accuracy. So there are three algorithms we'll focus on. So an algorithm order 7 and 6. So it's an adaptive algorithm. that dates from July 2024. An algorithm with order 8 and 7, and an algorithm with order 9 and 8. And as you can see, the coefficients have been derived very recently, so there is still a lot of active research in that domain. Because finding coefficients, like in the book of Butcher, he explained how to find coefficient, and it relies on a lot of complicated math related to actually tree structures and graphs. But all of that to say that it's not easy to find these coefficients. So Vernoth methods are explicit adaptive runge-kutta schemes, and it's a slightly modified methods with interpolants. Because the problem is that with adaptive method, generally, you cannot choose specific points where you want to have the value. For example, if your algorithm choose to integrate at point, let's say 1.2 and 1.5, and you want an output at 1.3, then it's complicated to do that. But the good thing with these methods is that for free, not exactly for free, but you have a very well-behaved method to interpolate in between the time step. So if you want specific time steps, this is a very useful thing. And there is a paper dating back from 2009, which is very nice, it's very clear, very understandable. And what it says is basically, for each time step yn, if you want to reinterpolate within the time step, you just need extra coefficients, which are the bi. And you have the u parameter, which varies between 0 and 1 inside the time step. So the kind of things you can find on the website, so this is a very old school website, but you have files with all the coefficients. And so your entire runge-kutta method is specified by these coefficients. And as you can see, maybe there are very short lines, and very short lines correspond to coefficients that are set to 0. And there are quite a bunch of zeros in these methods. So the software architecture we can design based on that. We can, as I said, we can derive runge-kutta, we can abstract runge-kutta method in software, basically with a small number of arrays. So AAJ, which will be a 2D array, the weights. So it will be a sequence of array, because if we have one sequence of weight, then it will be non-adaptive. For adaptive algorithm, you will generally have 2 array of weights. Then you have the nodes, which is it's not a sequence of 1D array. It is a 1D array. But the interpolants are a sequence of 1D array, because you will have a sequence of 1D arrays for each of the B. Meaning that if you have a method, a runge-kutta method that is using order 8 and 9, then you can interpolate using a method that is also 8 and 9, of order 8 and 9. So the general idea is that we would like to have something that will make a runge-kutta method from the coefficient, the weights, the nodes, and the interpolants. And probably some other parameters, but that would be very nice if we had something generic like this. So what we would like to do is, from this coefficient, then being able to generate at compile time all the ki to try to optimize them at compile time, and have the nicely put structure in the compiler so that the compiler can optimize that. So there are some performance concerns, because the Butcher tableau can be very sparse, as I said. And what it means is that some of the BI can be null coefficients. And if we want to implement methods where we start to have non-null that will behave differently with null coefficient and non-null coefficient for the user, it will be very weird and very not very practical for the user to specify. So what we would like to do is to design something so that the null coefficient and the null values are optimized away, and that so the user can just use an MD span for the coefficient, and the null coefficients are like not taken into account in that. And yeah, the reason why compilers may not be able to optimize null value of coefficient is because floating point have special values. So if you multiply not a number by 0, then it will return not a number. So what the user would like to, it would be nice if the user could type something along this line, where, because then he could just take, the person can just take Werner's website with all the coefficients and just copy and paste them there. So something that will make a coefficient array based where you would specify the indices of your value and then the value of your coefficient. And what would be nice is that if you just had to specify non-null values, because all other null values would be considered as 0. So the way we can have this kind of syntax is by creating an indexer type, which will do some magic in terms of expression template, meaning that if something is of indexer type and has a coefficient on the right-hand side of operator equal, then what it will do is that it will construct an indexer expression with the index on the left-hand side and the coefficient on the right-hand side. And then we'll store the value of the indices inside this structure. What we can do also is that specify the starting point of the indexer by saying that the indexer will have an operator bracket, and it will, where you can input, as you see in at the beginning of the slide, where you can input the values of the indices. And then what we can say is that we have an indexer that is just an instantiation of this indexer type. So if we do that, then what we'll end up with is we'll be able to achieve that, and it will be converted into an indexer. So if the user types that, then the type it will return is an indexer expression with, on the left-hand side, the value of an indexer, and on the right-hand side, the value of the coefficient. And if you want to, if you are interested into implementing this kind of expression templates in a nice way, because I don't have time to dwell into the details, you can look at the talk of last year, because I implement things in kind of a similar way, so the approach can be very similar. So there is a problem with the make coefficient array, because we would like to have a unique order, which means that if the user types first the index 0, 0 and the index 1, 0, and a user that would do indexer 1, 0 and then 0, 0, would like to have the same type. So having it to collapse to the same type would be very, very nice. So in that regard, C++26 will help. We can do this thing in C++23 already, but this is a lot of code. But in C++26, we'll have something that we'll probably have something that will allow us to have an ordering of our types at compile time. So when you are doing template metaprogramming and you want to collapse structure into a unique type, that can be very useful. So then about the indexing strategy, what we'll do is that the indexer expression we showed before will generate an indexed coefficient, which means a coefficient at a particular position. And then the indexed coefficient will have an accessor operator that will return what we call a numeric constant. And what we'll do with numeric constant is that the numeric constant will hijack the compiler's arithmetic. So the outline of the code for the index coefficient is that it's just a structure on the left-hand side, and the first parameter is the index, the other parameter is the coefficient. Then it has just a bunch of constants and types. It has an index type and the coefficient. And it has an operator bracket where you give it the index type, then it will return the value of the coefficient. And if you give it the operator bracket, then it will return the coefficient type itself. And what's interesting here is that the index type at compile time has to match the index that was provided, which means that these operators will be implemented only for the right index. Which means that then you can build a coefficient sequence where the operator bracket will be inherited from the right coefficient with the right index, and through overall resolution, it will redirect to the correct index coefficient. So then we want to hijack the arithmetic. So the way we'll do that is we'll have the numeric constant with some like constants and values. It's like the integral constant in C++, in the standard library. So it has kind of the same functions as integral constant. We have a helper that will make a numeric constant from a value. And then what we'll do is that we'll say that we'll specialize things when the numeric constant has a value of 0 in the right-hand side. And then we'll have a structure that will help us detect whether this is a null constant. So the reason we cannot all the time detect that 0 is that if the user has like specific arithmetic type, comparison to 0 sometimes for user type may not be entirely well defined. So the library, the standard library can do that with CMath to test whether the value is not strictly less than 0 and not greater than 0. This is most for like specialized types and regular types. And then we'll have a type trace that will return whether the constant is null or not. And then what we'll do is that we'll overload the operators so that when there is a value of 0 either on the left-hand side of operator plus or right-hand side, then it will just return the value that is not null. So we'll add a bunch of overload, and what we'll do is that when one side is a null constant, when both sides are not null, then we'll return a numeric constant of v1 of the two added values. But when one of them is null, then it will erase the null value and just keep the non-null value. So we can do all the overloads to also be able to handle things that are not numeric constants, so that we guide the compiler to optimize away values that are null. And we do that with plus, we do that for all the other operators. And what we do in the end is that we are rewriting the arithmetic rules for our solver. So numeric constant plus something, a null numeric constant, will collapse to the first one. And for example, when we multiply, it will collapse to a null constant. And if we wanted to go beyond that, we could have a value category, which would tell you whether it would be finite, infinite, not a number, integer, whatever. And you could rewrite all the arithmetic rules using that. So it's doable in C++, but it's very, you have to write a lot of code to do that. I think it will be far easier to do with reflection in C++26 using meta-info and specializing and do a dispatch based on the info we are getting and the type. And instead of having to write all the operators by hand, we'll probably have to specify two or three versions of the operators, and that will work automatically. So if we do that, then the nice thing is that we have a very nice unified interface corresponding to a Butcher tableau. Coefficients are easy to specify, yet the formula can be optimized so that the spatial numeric values do not cause any overhead. And we can access these values through MD-span, and these can be generated for method coefficient even if it's sparse. And you can also, given a method, you can test whether it's an explicit or an implicit method and specialize on that based on the coefficients. So the compiler is doing all the work for coefficient that you specify as a user. So in terms of outlooks, something that would be interesting would be to combine symbolic computing strategies like the one I showed last year to be able one day to write things like this, where we could write like solve, for example, on GPU, and then we would write our symbolic equation and with our solver. And the compiler should be able to like derive everything and to take and to combine the right runge-kutta solver to compute, to solve the right equation, the right symbolic equation, and the right CPU or GPU or accelerator. In terms of science outlooks, so with that, even if it's simple, like ordinary differential equation are something like very easy to solve these aren't complicated. We can do interesting things in terms of science because we can use the same solver to actually compute the space-time geometry and the n-body dynamics. And for example, we can try to see what happens in an n-body system where you have a global constant curator for the universe, because generally what happens is that algorithms that are used on supercomputers today use very different methods because n-body systems are very complicated to solve and without simplification. But because of that, because you have special boundary condition, it's not generally easy to solve this equation on a global curator that is not flat. Which brings me to my conclusion. So the most important thing that I want to highlight in terms of software architecture, that the best software abstraction are generally derived from well-posed mathematical abstraction. And conversely, if your problem is not well abstracted in terms of math, then maybe we will not manage to abstract your problem. And sometimes it can be linked by the fact that you are missing some strong mathematical foundation. So ordinary differential equation solver is a very good exercise to implement on your own. Like the first example I showed in the first part of that talk are like less than 100 lines of C++, and it gives you a good impression of how they work. The methods are well abstracted in mathematics with 3 classes of methods: runge-kutta, LLM, and GLMs. Runge-kutta method can be represented as Butcher tableau, and more abstract than that, the GLM can be abstracted by a tableau of 4 matrices. And the implementation outline we showed here is that it relies on coefficient multi-arrays and that allow the user to specify them in using a intuitive syntax. And even though the syntax is intuitive for the user, then we'll hijack the arithmetic to remove the operation that are not necessary. And then we can generate the integration steps from these non-null coefficients. And in terms of outlooks, we can continue to implement that and try to combine it with symbolic computing methods. And there are interesting scientific use cases, even with simple integrators. And thank you very much for your attention. I hope you learned some stuff. And if you have questions, then I'm here to answer them.
Thanks for the talk. It was really interesting. I did have one question about when we were doing the indices and we needed a canonical ordering of types.
Yeah.
Which is the kind of thing that sounds really easy, but anyone who's ever tried to do it in C++ knows that it is not. This comes up in the units libraries, for example. it seemed to me that maybe for this one, we didn't need C++ 26 or 23 because it has 2 numerical values.
Exactly, yes.
It's actually, I wish my case was that easy.
No, exactly. And actually, in my own library of units, when I play with example, what I do is that for every type, I write an ID, an identifier, and then I order them because it's currently complicated to do that. But in C++ 26, we should have something to do that in arbitrary types.
Yeah, I saw that paper coming. I was very excited
Yeah.
for that. Thanks again for the talk.
I guess my question real quick was, have you seen this generically bounded approach where you're starting with the very generic version of this implemented anywhere else, or is it kind of new?
So it's not new, but I think the ones that... So I didn't delve into the code of Julia, but I think they are implemented in this kind of way because as I said, they probably have more than 100 different methods. So they needed a generic way. And my guess, I didn't look at the code, is that it's probably implemented in that way. Or maybe they have a specialization for runge-kutta, a specialization for LMMs, and a specialization for GLMs. But my guess is that they pretty much do it in this way. Okay. Thank you, everyone.